Hello everyone, and welcome to another lecture in Computational Algebraic Geometry. Today we'll be talking about one-dimensional schemes, so these are curves. So let's be precise about what I mean by a curve. So a curve will be a smooth projective variety. So the projective variety part just means it's the zero scheme of an ideal in Pn. Smoothness we've defined for hypersurfaces, but never mind, we can talk about plane curves in just a second. And then the crucial property of a curve is that it's dimension 1. And I don't want a union of such objects, I want something that's connected, irreducible, or to say it properly, we have to say it's geometrically connected. So we're trying to get an intuition for these objects. I just don't want disconnected components. Normally the condition on smoothness can be relaxed when talking about a curve, but I do want something dimension 1 and I want something algebraic. That will be a curve. And one important example that we can talk about will be hypersurfaces in P2. So as we discussed, these things will have codimension 1 and therefore dimension 1, and we know how to check for smoothness, so this is certainly a good example for curves. So the notion of dimension is very tricky. So this was simple when dimension was 0, and this was a bunch of points, and we've spent a lot of time with dimension 0 schemes. Now we're talking about dimension 1 schemes. Since we didn't give a formal definition of a dimension, let's study the case when we're studying, let's say, curve defined over a field of characteristic 0. So K is a field, so C is a curve defined over K means you can find generators for an ideal where the coefficients are in K. And let's suppose that this K can be embedded into the complex numbers. So in particular, the characteristic of K is 0. Well, then I can talk about the set of complex points on C. So as we talked about hypersurfaces, this thing will be a complex manifold of dimension 1. Since I assumed smoothness. But, so this is the complex dimension is 1. If I were to view it as a real manifold, and this thing has to be of dimension 2. I mean, the complex plane, for example, is one-dimensional over the complexes, but two-dimensional over the reals. So the dimension multiplies. So the scheme theoretic dimension gives you this dimension, the complex dimension, or the dimension over an algebraically closed field. And we can get two more things here. So C, or the complex points of C if you want, is compact. So that's this projective part. So it's oriented. So this is, if you know what orientation means, real manifolds don't have to be orientable. So for example, a Mobius strip cannot be oriented, so the strip doesn't have an upside or a downside. You cannot consistently choose one anyway. But whenever you have a complex manifold, it's always oriented. And if you forget the complex structure, then it's orientable. Okay, so and we can view it as a real surface. By the way, this is sometimes called a Riemann surface. Riemann surfaces can be more general, they don't have to be compact, for example. But anyway, so there's always this discrepancy of being a complex curve and a real surface. So now let's benefit from this real structure and use the classification of compact, orientable, real surfaces. So this classification theorem says that any compact, orientable, real surface is diffeomorphic, homeomorphic, whatever the structure is here. So this surface will be diffeomorphic to one of the following representative objects. So you can have a sphere, you can have a torus. This is a torus, or the surface of a donut. So here you may have a loop here, for example, and a loop like this to represent the geometry of this thing. Or you can have two of these handles, or three. They don't have to get smaller, but I'm running out of space, and so on. And usually we say that the genus of the sphere is 0, of the torus is 1, 2, 3, and so on. And the way we're going to use this classification is to say that so the genus of a curve, again defined over a field with K in C. First of all, we'll write GC for this genus, and it will be the genus of the underlying real surface. So the theorem upstairs says that this set of complex points, this real surface, is either a sphere or a torus, 2 torus, 3 torus, 4 torus, etc. So its genus is some non-negative integer, and this non-negative integer is the genus of the curve. For example, the genus of P1 is going to be 0 because P1 of C, we've discussed this before, is a sphere. And we talked about x squared plus y squared equals z squared inside of P2. So in one of the first lectures, we've shown that the set of complex points of this curve is also homeomorphic to a sphere. So the genus here is 0. Well, let's do a small digression into this classification of surfaces. So I talked about the genus being possibly 0, 1, 2, etc. So I want to give here models that are perhaps easier to visualize. So instead of 3D models, I'm going to give 2D models. So here I take the inside defined by this, well, essentially a circle. But what I'm going to do is that take this edge and identify it with this edge, with the same direction. For example, what happens is that if you walk in this direction, you would come back here and connect back to yourself. So that if I were to think of this thing as an elastic surface, and I take the two ends and glue them together, just prior to gluing, it might look like this. So okay, I stretched this and I'm about to glue them. So this is what's about to become a sphere. And for genus 1, what you do is you use 4 edges instead of 2. You identify the opposite edges. And again, you take the interior of this thing. So here, if you were to identify the opposite edges first, you would get a cylinder. So maybe my 2 edges here prior to gluing are these parallel lines, and they will glue and become a single line. And these 2 circles, these 2 ends are still to be glued, and once you glue them, you get a torus. So these green edges become these 2 circles, and when you glue, you get a torus. And now the general pattern is that so for genus 2, I would take an octagon and again identify the opposite edges. And when you have G handles, you're supposed to take a 4G gon and identify opposite edges. So these 2-dimensional representations, I mean, things that you can lie down flat on a plane, are sometimes easier to work with and easier to think about. These blinking tori are very nice to visualize. They're slightly more true to the origin, but they might be harder to work with when making topological arguments. Okay, so let's end this alternative representation and talk about plane curves for just a moment. And there's a theorem that we will come back to later on in a later lecture. And this theorem states that if C is a plane curve, so in particular if C is of degree d, then the genus of the curve is d minus 1 choose 2, or d minus 1 times d minus 2 over 2. So let me be clear here. C is the zero locus of a polynomial f, and the degree of f is d. So in other words, in this case, this rather transcendental construction has a purely algebraic description. So let's collect some of the simple examples. So if I take a line in P2, then the genus is 0, d equals 1. Genus of a conic, so d equals 2, is 0. And before we mentioned genus of P1 is 0, so that's just the embedding of P1 as a line. G of conic, so I mentioned upstairs the complex circle, so that was a conic, that has genus 0. It turns out that, of course, conics are also isomorphic to P1s. And then G of a cubic, which means d equals 3, is 1. So here we have something like torus, whereas G of a quartic is 3. And you see the formula is quadratic, so we're not going to hit every integer by just increasing the degree. Nevertheless, it's true that there are curves of every genus. Although, obviously, no smooth plane curves of every genus. So we can be a little bit more precise here, and it's a very interesting story that we will not entirely pursue. So we can So there are spaces that parameterize every curve of genus G. So these are called moduli spaces or parameter spaces. So these are algebraic varieties. And they're usually denoted by mg. And what I'm saying with regards to being a moduli space is that in particular, if I plug in C here, so if I'm looking at complex points of this algebraic variety, then this is sort of canonically in bijection with all curves over the complex numbers and up to isomorphism. So very roughly, we consider something like a set of all possible curves over the complex numbers, and then we mod out by isomorphisms. So the set of isomorphism classes of all curves over the complex numbers of genus G is canonically in bijection with the set of complex points of Mg. So we know the dimension of Mg. So the dimension is 3G minus 3, and this holds true only if G is at least 2. The dimension is 1 when G equals 1, and 0 if G equals 0. And Mg is irreducible, so that means every curve can be deformed to one another. So every curve of the same genus and given a curve of genus G, you have 3G minus 3 directions to deform it. That's more or less the dimension of Mg. So the irreducibility is sort of more or less classical, but the modern proof, which is a little bit more comprehensive than what I've written, is due to Deline and Mumford. So now I've given a definition for the genus that was about trying to understand the geometry of its complex points of a curve. So I used these pictures. On the other hand, when you ask, let's say, magma for the genus of a curve, it will answer. So it doesn't plot its complex points and look at the picture. So there's actually a better way to define the genus. So better in terms of a more algebraic definition. It has two advantages. First, it becomes more computable. The construction of an expression like this has a very simple algebraic interpretation. And we can handle another issue where we've been talking about curves that are defined over fields that are embedded in complex numbers. In fact, no such restriction is necessary. Even your base field can have an arbitrary characteristic, so you can perhaps never go up to complex numbers. Nevertheless, you can define genus. So there's a more algebraic definition of genus, and this goes through a theorem due to Riemann that identifies the genus with the following. He says that the dimension of the genus is the dimension of a particular vector space, and this vector space is the space of global sections of the cotangent bundle of the curve. So in the next lectures, we will talk about this object, the cotangent bundle in its sections. But in particular, this construction is well defined even if C is defined over an arbitrary field. Okay, so I will end this lecture here, and I will see you in the next one where we talk about the cotangent bundle.